Welcome to a code report solution video. In this video, we're going to be going over the solution to problem 2 from topcoder SRM 732 entitled CubeStackingGame. The problem states you recently designed a cube stacking game. This is a single player puzzle. All you need to play the game is a collection of cubes as described below. You have n cubes. The cubes are numbered from 0 to n-1. Each face of each cube has a single color. There are n plus 1 colors. One of the colors is white and has the number 0. The remaining colors have numbers 1 to n. Each cube has exactly 2 white faces, and these are always opposite to each other. Let's number the remaining faces on each cube 1, 2, 3, 4 in adjacent order. That is, face 1 is adjacent to 2, 2 to 3, 3 to 4, and 4 to 1. For each cube, you are given the colors of these 4 faces. On cube I, these faces have colors C1I, C2I, C3I, and C4I in order. Remember that these faces are never white. You want to build a single stack of cubes with cube 0 on the bottom, cube 1 on top of cube 0, and so on, i.e. you have to use the cubes in the given order starting with 0, and you are not allowed to skip any cube. The cubes have to be aligned to form a single stack with 4 vertical sides. You may rotate the cubes arbitrarily, but you must place them onto the stack in such a way that the top and bottom face of each cube will be white. On each of the 4 sides of the stack, each color can only appear at most once. Calculate and return the maximum height of a valid stack that can be built out of the given cubes. And note that for this problem, n is going to be quite small. It'll be between 2 and 8. And each of the vectors C1 through C4 will contain exactly n elements, and each element of the vectors C1 through C4 are going to be between 1 and n inclusive. So let's take a look at an example and see if we can understand this problem a little bit better. So here we have our example, n equal to 4, and we have 4 cubes described with the vectors C1, C2, C3, and C4. So you can think of each one of these columns across our vectors is going to represent a single cube. If we create a color legend, so 1 will be red and 2 will be yellow, so on and so forth, we can create a visual representation of what these cubes look like if they were flattened out. So you can imagine if you were to fold this into a sort of square and add 2 white sides on the top and the bottom, you'd get your cubes. And so what the problem is asking is, what's the maximum height we can get by stacking these cubes such that every face of that stack only contains 1 color? So if we were to stack these 4 cubes on top of each other, given its starting orientation, let's call it, you'll note that this face would have 2 reds and 2 greens. This face would have 2 reds. This face would have 2 yellows. So we want to rotate these cubes in order to maximize the possible height that each of the faces only has 1 color. And the way we're going to do this is with a simple depth first search. So the solution to this problem is actually quite simple. It's more the implementation of it that's the tricky part. So let's see how this will work. So we get rid of our 3 blocks and we start with our starting block, and at this point we know our maximum height that we've reached is 1. So anytime we can successfully place another block on top, we are going to increment this guy. Or basically this is going to be globally set, and then every single time we're going to set it to be the maximum of its current value and the new total of our height. So we'll get our next cube, and you'll see here that we're going to check, okay, there's only 1 of each color, but we have conflicts here. So we have 2 yellows. So at this point we know we can't add the cube in this orientation. So we are going to rotate that. And what that'll look like is bringing the green face over here and then shifting everything else to the left. So let's see what that looks like. So now you can see that we only have 1 color in each face. So the red the yellow no longer conflicts with the yellow, and this red doesn't conflict with these reds. So we can at this point set our height to be equal to the maximum of what it was, 1, and its new height 2. So this will be now 2. Then we grab our next cube, and luckily, based on its current orientation, this doesn't conflict with anything either. So we can right away set h equal to 3. And finally, we grab our 4th block. We'll see that we have a conflict with our first face because we already have a red. So we're going to rotate this, but we still have a conflict. So we'll rotate it again. We still have a conflict. We'll rotate it again. And on our final rotate, we still have a conflict. So note that once you've rotated it 4 times or 3 times to get the 4 different orientations, you also need to flip the cube. And so you can flip it by reversing your colors and then rotating through them again. But note, because this is symmetric, we don't actually need to, well, we'll do it in the code, but I'm not going to show it here in the visual example. So we would get through all 8 different orientations of this cube, and then we would end up popping it off. And we would do the same thing here, but we'll notice that this is the only successful orientation because red will conflict with these 3 faces here. So we'll end up popping this one off, and so on and so forth. So if you continue to do this algorithm, this depth first search, you'll end up with your global answer h equal to 3, which is the answer for this problem. So let's take a look at a couple different solutions or ways to implement this algorithm. So we have the code split up into 2 columns, but you can think of the right column going beneath the column. And so we've got 3 different functions here. We've got our main DFS function, we've got a modify, then DFS function, and we've got our function that the problem asks us to implement. So it gives us an integer n, the number of colors / blocks, or I guess the colors are n plus 1 if you include white, and then the 4 vectors that represent the cubes. And so what I've done up here is I've just declared some global vector ints and unordered sets of integers so that we don't need to pass these around everywhere. You know, in production code, you definitely don't want to do this, but for competitive programming, it's okay. And so we're going to initialize our vectors of integers to be equal to our color inputs, and then our global n equal to n, and then we'll call DFS 0. So then we'll come in here. Each time we enter a call of our DFS function, we're going to set our global result res to be equal to the maximum of what it currently is, and the depth that or the height that we've currently reached, which is I. And if at any point I equals our total height, we know we can just return out of this. And then what we're going to do is we're going to call this function modify stacks, then DFS, and we're going to pass into it I currently. We'll do the I plus 1 over here. And then we're just passing in the 8 different orientations of the cubes. So this is not the most, cleanest way, I guess, to do this. We'll see in a different solution you can put this in a loop. But in terms of implementing something quickly, you can just copy and paste this and then move. We start with E, F, G, H, and then we bring the F to the left, the G to the left, the H to the left, and then we put the E at the end, and then we flip at the middle point here. So you can see that H, G, F, E is the reverse of E, F, G, H. So that's when you're flipping the cube upside down. So when we enter this function, what we're going to end up doing is first checking to see if there are any of the colors that we're trying to add. So when we add this cube to our stack, are there any colors currently on that face? And so that's what the unordered set of integers are. So we can use count, which will return us 1 if the color exists and 0 if it doesn't exist. And we want these all to return 0, saying that none of the faces contain the color that we're trying to insert. And if that's the case, then we can insert each of these, store the iterator that points to the element that we just inserted in the unordered set, and then we can call DFS with our new sort of updated stacks. We add 1 to our depth, and then once we exit this function, we want to erase those iterators. And using this, we're going to get our correct solution. So this is not obviously the prettiest because we have a lot of copied code here. We've got the same line just applied to different things. So here is an alternative solution that's a little bit harder to follow, but it doesn't have the same lines over and over and over again. So here is our alternative solution. Note that we aren't using an unordered set anymore. Now we are using a vector of vectors. This was pointed out by Dennis when he was reviewing the code. He pointed out that you don't actually need to use an unordered set and the count and inserts. You can just use a vector sort of acting as like a bit set, and you can just turn on the elements corresponding to the colors 1 through 8 by setting it to 1, and then afterwards setting it to 0. So instead of using count, then insert, and then erase, you can just use this vector, do a bracket lookup, and then set equal to 1 and 0. So here we're doing the same thing, setting our global vectors equal to C1 through C4, and then we declare our vector of vectors, which will be our stacks. And we can then pass this in because it's only one of these guys. There's not A, B, C, D as there was before. So we pass this into DFS, and then we do the same set for results and our same return for I equal to n. But at this point, instead of doing those 8 different calls to modify, we are declaring a vector of integers c, which is our colors, and then we're setting them equal to the initial state of our, what was c1, c2, c3, and c4. And so at this point, we can then call a for loop that loops from 0 to 7, so 8 different ways. It'll originally pass in modify, and then after each modify call, it will rotate the vector. So what that's going to do, it's going to shift everything to the left by 1 and put the first character, the first element at the end. And that's because the way that rotate works is it takes whatever iterator you give it here and it moves that to the front. And so that way we can sort of generate the 8 different orientations combined with this reverse. So at the midpoint, when j is equal to 4, we want to reverse our colors, and that will give us the 8 different orientations. So on top of that, once we enter modify, we have the same idea that we had before, but as I mentioned, we're using a vector now. So we set our Boolean perform DFS. If there's none of the colors, when we do that by looking up the color which is stored in stacks, we're going to end up coming in here and doing the same thing, but like I said, not using insert and erase, but just setting equal to 1 and then setting equal to 0, and this will also work. And the last thing to mention is the time complexity. Because we have 8 recursive calls within our recursive function, this is going to be 8 to the power of n, or in other words, big O of 2 to the power of 3n, which is just going to be inside our time limit. Also, a big thanks to Dennis for reviewing these code solutions, on top of which he also coded his own C++ 11 and 17 solutions. So if you'd like to check those out, I will leave links in the description down below.
As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.